Good morning everybody. In the first lecture I had talked about concept of steel quality and what are the cleanliness requirements. Basically I had mentioned that by quality of steel is meant what that it is should conform to specified application requirement, that is the definition of quality of steel. That means for every quality there is a specified application requirements. Quality for a particular application requirement may not be same as the quality requirement for a different application. So, we have to keep in mind that. Then I had talked about what are the quality attributes, like how we measure quality by looking at what we tell that quality is good or bad, or what are the issues which we should give importance to. So, I had mentioned that there are certain issues like metallurgical quality, certain issues like physical quality. In this lecture I will be mainly harping on metallurgical quality. So, by metallurgical quality what are the attributes? The specified chemistry, that means every steel must have a specified chemistry range, that is what is required for the particular application. So, this is very important, specified chemistry. Next, the residuals and trace elements should be low. I had mentioned what is meant by residuals. Residuals is different from alloying elements. Alloying elements are which are intentionally added in steel for getting certain properties, required properties, but residuals are those which are not desirable in steel, but they are there because of the steel, by the way the steel is processed or produced. So, they are called residuals, they are not required, but some amount will be there. So, this has to be low within certain limits. Then there are trace elements, again these are not required, but this where from this will come, we will discuss all these issues. Then the defects, whether it is on the surface or internal defect, these details will be discussing one by one. This should be minimum. So, these are all requirements and these depend on the application specific. These are all application specific, that means depending on the particular application of the steel, all these are identified, all these are defined. Next important aspect is the cleanliness, that means the steel must have certain higher limits of constituents which make it dirty. They can be micro, that means very small in size, or there can be macro, that means larger in size non-metallic inclusions. So, these are very important. Then desirable microstructure and properties, of course, this is definitely one important requirement, because without that the steel will not serve the purpose for which it is being meant. Now, where from these are coming, these undesirable factors like the residuals, trace elements, defects, cleanliness issues, these are basically inherited either from the parent cast material, that means they are intrinsic to the material, from the way the steel is made, the way the liquid steel has been prepared, or it has been cast. So, what are the quality issues there? What are the cleanliness level? What are the defects which are produced during casting? These are the issues which are inherited from the parent material. So, this is very important, or some of these quality issues may be imparted during subsequent processing. Now, the first one, that means inherited from parent cast material, I will be talking in this course mostly on this issue. So, this is what is important. We have to keep in mind the whole purpose of this course is to highlight the quality issues which are inherited from the parent cast material, that means from the liquid steel, how it is made, refined, or during casting what are the quality parameters, what are the quality issues. These are the important aspects which I will be highlighting in this course. And the next one, that means imparted during subsequent processing, that means the processing defects I will mention once or twice, but that will not constitute the main issues, main subjects of this particular presentation or talk or course. Then under quality issues of material origin, I had mentioned how they are manifested. They may be manifested as surface imperfection, that means they are visible with normal eye, or certain special tests are necessary to make them visible. There may be crack which is visible, there may be lamination, that means a surface defect, something different from the normal surface, something coming out or getting manifested on the surface. These examples I will give in today's presentation. Or it may be a sliver, that means very thin inclusion like defect, very thin but adherent to the surface, this is called sliver. Maybe NDT failure is a quality issue. NDT failure means non-destructive testing, through which we come to know what are the internal defects, internal imperfection. Now, these are the two major issues, the surface imperfection, surface of subsurface, that means which are almost visible to the surface, either normal eye or with some special tests. I will discuss these issues. But defects which are inside the product, these are called internal defects or internal imperfection, they are normally revealed through non-destructive testing. So, through that, if there is a failure, that means non-destructive test tells you that the defect size is more or the defect incidence is more, then normally it is called NDT failure. It indicates that the internal defects are relatively high in intensity and the product quality is not to the desirable extent. So, we call it NDT failure, that means failure due to non-destructive testing. Now, these are the manifestations. Now, where from this can come? Again, there are two major issues. First, the poor cleanliness of the steel, that means the entrapments or non-metallic inclusions, whether they are coming from the exogenous sources or during the steel making process, that is very important. So, related to these are basically related to refining and casting process. That means, when you are making the steel, then you are refining the steel, you are bringing down the undesirable residuals, you are bringing down the undesirable constituents, inclusions. So, during that process cleanliness level is enhanced. So, if it is not enhanced to the desirable extent, then certain cleanliness problems may remain, and that will constitute the main quality problem. Second most important is the surface, subsurface or internal quality of casting. Maybe the cleanliness is okay, but during casting, during continuous casting or during ingot casting, certain defects might be generated. Maybe it is related to the specific grade, that is intrinsic to the particular grade or chemistry, or the casting process may not be all right. The casting process may be prone to defects. So, the grade may be responsible, or the casting process may be process parameters may be responsible. So, we have to be careful about those. Now, I had mentioned earlier and again I am repeating, these cleanliness requirements are application specific. That means, the residual impurities, I had mentioned what are the residual impurities, they can be sulfur, phosphorus, oxygen, nitrogen, hydrogen. Please notice that these are not desirable elements or alloying elements in steel. That means, these are all residuals. We do not want them in steel, but because the way the steel has been produced, some of them they get inside steel, remain within steel, sometimes they become beyond the desirable limits. So, that is very important. Then NMIs or non-metallic inclusions, they can be oxides, different types of oxides, SiO2, aluminum oxide, manganese oxide, or silicates, that means SiO2 MnO combined, Al2O3 SiO2 combined, aluminum silicate, or manganese silicate MnO SiO2 combined, or it may be sulfides, manganese sulfide, calcium sulfide, different sulfides, or nitrides, they may constitute non-metallic inclusions, iron nitrides, vanadium nitrides, titanium nitrides, different type of nitrides. Then what are trace elements. This is very important. Again, these are not desirable in steel, but they come from the scrap, from the source of starting materials with which you are making steel. There may be arsenic, antimony, tin, copper, lead, zinc, tellurium. This depends on the source of the scrap, where from we are getting the scrap. So, this is very important. These elements, trace elements, normally do not come from the iron ore, natural sources, but they come from the scrap. That means the steel which have been scrapped, that means the quality has been bad, or due to some any reason they have they have got generated during steel making process, there are some oxides. So, all these scrap elements or scrap materials with which we make steel, we make steel in electric arc furnace or induction furnace, they are known as trace elements. These have to be present within certain limits, otherwise they can constitute cleanliness problems. Now, that is amounts, chemistry, size, distribution of the non-metallic inclusion, this is very important. Naturally, their amount has to be within certain limits, there are higher limits depending on application. What are those NMIs? That means the chemistry of NMIs, what are they? Are oxides, sulfides, oxysulfides, silicates, that is very important, because the behavior of the inclusions will depend on the chemistry. Size is very important. If they are very small in size, they are benign, that means they are not harmful, they are relatively harmless, may not constitute a defect. But if they are larger in size, say more than 50 micron or 100 micron, then it is a problem. They might create a lot of defects. And the distribution of these non-metallic inclusions is also important. How they are present in steel, whether they are present as a chain or they are present as discrete separate elements with a distance, that is very important. If they are present in a chain, then it may not be desirable. If the interparticle distance between the inclusions are less, then it may be a problem. So, the desirable microstructure and properties, surface and internal quality, these important requirements of steel are very much dependent on the amount of inclusions, the types of inclusions, the size of inclusions and their distribution. Now, in today's presentation, I will be giving you certain typical examples of surface defects. I have told you in general what is meant by steel quality, how they are manifested as defects on the surface or internal, and what are the reasons, what issues or what parameters are responsible for the generation of these defects. Now, I will give you certain typical examples from which we will come to know, or it will be easier for you to understand or comprehend what are surface defects. Now, I will give you few examples which are known, very common surface defects in steel. We may come across in different occasions, and these are quite common. That is why we have chosen few such typical examples of surface defects. First, let me talk about edge crack in hot rolled coil. The cast slab, continuous cast slab is hot rolled in the form of plate or coil. So, when the thickness is less than 10 millimeter, maybe 8 millimeter, 6 millimeter, 4 millimeter, 3 millimeter, 2 millimeter, this hot rolled material is called a hot rolled coil, because this is relatively thin, it has to be coiled because it is quite long. So, it does not have the strength to remain steady, so it is normally coiled, and plates are relatively thicker in size, maybe more than 10 millimeter, maybe 15 millimeter, maybe 20 millimeter, 25 millimeter, 30 millimeter, 40 millimeter, 50 millimeter, 100 millimeter maybe. So, those are called plates, hot rolled plates. Now, in hot rolled coils, that means relatively thinner hot rolled materials, less than say 8 millimeter or so, we may get edge crack. That means crack at the edges. That is a typical example of defect in steel. I will come to it, I will show you a figure how does it look like. Then there may be a transverse crack on hot or cold rolled surface. Transverse crack means it is transverse, that means perpendicular to the direction of hot working, that means whether it is hot rolled or cold rolled, direction perpendicular to that you might be having certain cracks, those are called transverse cracks. Then we may get surface lamination, that means these are in longitudinal direction on hot or cold rolled coil or plate, you call surface lamination, that means as if something is coming out from the steel surface, there is some discontinuity in the surface, that is called lamination, as if some additional surface has been generated, some linear longitudinal looking additional surface which is sort of coming out from the actual steel surface. I will show you certain figures, you will come to know what is surface lamination. Then there can be sliver or thin line in longitudinal direction on cold rolled coil. Cold rolled coil, basically why I am talking of cold roll, because it is very thin material, maybe 1 millimeter, less than 1 millimeter, 0.5, 0.2, 0.3 millimeter cold roll material, that means very thin material. You will find this defect which is a very thin line and it is adhering to the surface. Surface lamination as if it is coming out from the surface, but sliver or thin line which is adherent to the surface of the cold rolled coil is known as sliver or thin line of, some people call it thin line of non-metallic inclusion. Okay. So then there can be a surface tearing or hole in cold rolled coil, that means as if the surface is coming out, which is normally in transverse direction. It may be hole, it may be a tearing. Normally it has been found, I will discuss this in details, it is due to mechanical processing, too much of severe deformation that is creating this problem. The other ones, edge crack, transverse crack, surface lamination, sliver or thin line, they are mostly due to material problems as I have mentioned, but the surface tearing or hole is basically essentially mostly due to processing problem. Now let me show to you how these different defects look like. This is an extreme case of severe edge crack, that means it is a coil say about 4 millimeter or 3 millimeter or maybe 5 millimeter HR coil, hot rolled coil, which has been displayed here. It is from austenitic stainless steel. Sometimes we find severe edge crack or incidence of edge crack, that means the edge you will find is not smooth. Sometimes people call it edge check also, that means there is a crack formation at the edges of hot rolled coils. This is typical in austenitic stainless steels. This has been evaluated, this has been a lot of investigated. So, we now know what is the reason. I will discuss this later on. I had talked about transverse cracks. Now, this is what it looks like. These are perpendicular to the rolling direction. You will be finding certain cracks transverse to the rolling direction, perpendicular to the rolling direction. It is normally on the hot rolled or cold rolled plates, or even in coils it might come. Then I have talked about surface lamination. Now this is a typical surface lamination. As I had mentioned, it is something as if it is coming out from the surface. There is some discontinuity with the surface. So this is again longitudinal direction, this surface lamination. In hot or cold rolled steel surface you can see such defects. You can see that it is something which is as if coming out from the additional surface has been generated. So this is called surface lamination. It is a common defect in hot rolled coil, and it has been found, I will discuss this, that normally the origin of this defect is from either cleanliness problems or casting problem, or sometimes it may come during slab reheating also. So, these are the main sources or genesis of this problem. This I will be discussing. Now, I have talked about sliver, that means a thin line along rolling direction on cold roll surface. This is how it looks like. This is at high magnification, this is not at normal magnification. We are looking at it with magnifying glass, maybe a magnification of say 10 or 15. But if you look at a normal magnification, that means with normal eye, it is a thin line of rolling direction. How does it look like? So, now I have talked about surface tearing or hole on the surface of cold rolled coil. This looks like this. You can make out that the surface has got torn and finally it is generating sort of holes. So, these are typical surface tearings or holes during formation. They are formed during cold rolling, that means in cold rolled coil, in tandem mill, when you are doing cold rolling you can sometimes find this. These are, as I have mentioned, something to do with some difficulties or problems in cold rolling, maybe lack of lubrication, maybe additional deformation, something like that, nothing to do with the material problem. Now, I have shown to you certain typical defects, how do they look like, common defects, whether it is edge crack, whether it is surface lamination, whether it is transverse cracks, whether it is sliver or very thin line, or whether it is a surface tearing or say hole formation during cold deformation. These are typical and very common defects in steel. All of you who are associated with steel industry or you are using steel for certain applications, you must have come across such very common defects. Now, the purpose of my presentation is to give you examples of these common defects, and then I will discuss how these defects are getting generated. How do we investigate these defects? What is the purpose of investigation? For the purpose of investigation is to know what is the genesis of these defects, how these defects are getting generated. If we know how they are getting generated, then we know how we can take care of these defects. We know how to get rid of these defects, or we know if not completely eliminate these defects, at least how to control these defects within limits, within tolerable limits. So, that is what is very important. Now, how do you know what is the genesis of these defects? First and most important is, how do we investigate defect? There has been an incidence of defect, how do you go about it? How do you go ahead to identify what are the sources of defects? So, this is very important, methodology of defect investigation. What are the steps, one by one, how do you do, how do you go ahead? First is, we should know that when we are trying to identify the genesis of quality problem, it is basically a post mortem, that means already the steel product has been made and we are finding that there is a defect. So, that means it is a post mortem, the damage is already done, we have come to the damage stage. It is like a person who has been afflicted with some disease, that means the damage is already done, disease is already known, identified. So, now we are trying to know what is the reason of the disease. It is same thing, it is a post mortem, something has already happened, we are trying to analyze why it has happened. The better thing is, from this analysis, if we know what are the problems, then we should be careful beforehand, so that these defects do not occur at all. That is the ideal thing. We should be more knowledgeable about why these defects are created, these defects are getting generated, and we have to be careful during the making of the steel. whether in liquid steel or during casting or during processing. If you are careful, these defects will not get generated at all. So, that is what is more important. So, identification of genesis of quality problem in final product, that means already the product has been made and then we find the defect. So, this is essentially a post-mortem. So, we learn from this methodology how the defect have been generated, so that in future we can be careful, so which will help us in getting a better quality product and these defects do not get generated in the first place. Now, what we must remember is a specific cause may result in different symptoms. Like specific cause means, say, cleanliness is the problem in steel. So, poor cleanliness or dirty steel may result in different symptoms. It may result in sliver in final product, thin line of defect. It may result in surface lamination type of defect in early stage of hot rolling. So, what I meant to tell is that a specific cause, let me talk about, say, poor cleanliness, that means exogenous entrapments relatively of larger size. So, a specific cause, specific reason may result in different symptoms depending on how we are processing the steel, what is the steel. So, the symptoms may be different, but the cause may be one. So, we have to be careful about that, or different sources may lead to similar symptom. Again, let me give examples. I had mentioned one source is poor cleanliness. I have mentioned another source or genesis of defect may be cracks or problem in during casting. Now, both of these genesis, both of these sources, that means poor cleanliness or cracks in cast product, may lead to similar symptom, namely, I had mentioned about this defect, surface lamination. So, surface lamination we will find out may be due to poor cleanliness or it may be due to cracks, existence of cracks or certain other casting defects in the cast product. So, what I am telling is different sources may give rise to different symptom or similar symptom rather. So, the sources are different, maybe cleanliness problem, maybe large NMI, exogenous entrapment, or it may be a surface crack or some other surface defect in cast product, which may lead to surface lamination in the final roll product. So, what is important is this, that systematic investigation has to be systematic, it should not be random, it should be done in a very systematic way. I will mention what are the essential steps. This is very important, essential systematic investigation to diagnose the root cause. What is the cause? What is creating this problem? We are only looking at a symptom which is manifested at a small portion of the final product, from which we are trying to diagnose what is the root cause. Like when a patient comes to a doctor, there are certain symptoms, maybe the temperature is high, maybe the blood pressure is high, maybe certain other, maybe his headache is there. So, these are all symptoms, but the root cause, why this is getting generated, that is what the doctor is supposed to know, that is called diagnosis. Then he will diagnose from the symptoms, he will try to, from his knowledge, from his investigation, he will try to know what is the cause, what is the root cause of this disease. Accordingly, he will prescribe medicines. Similarly, we in our study, in our metallurgical investigation, we are looking at only the symptom which is manifested at a small portion of the final product. We have seen the final product, we have cut a small portion of the product, we have brought it to the laboratory, now we will start the investigation. So, we have only a small portion of the product, we have seen the symptom, the manifestation, that is the starting point. From our knowledge, we have to identify what should be the tests, how do we go about the investigation in a systematic way, how do we go about. So, from our knowledge, from our experience, we will formulate the investigation strategy, how do we go about the study, and then we will finally identify what is the root cause. So, it is like I have given an example, like a patient goes to the doctor, doctor tries from the symptom, whether there is headache, whether there is blood pressure, whether there is fever, or there may be other symptoms. You know, the fever may be one symptom, common symptom, but the reason may be different. So, the doctor's responsibility to know, depending on what tests or depending on his knowledge, why the fever is happening, why the temperature of the patient has gone up, why he is having headache, why he is having BP, these are all symptoms. So, in our product also defect is a symptom, it is a manifestation of a internal some other problem which has generated the defect. So, our role as a metallurgist, as an investigator, from the symptom manifestation, we should investigate properly and identify the root cause of the problem, and then we become more knowledgeable. Next, when we make steel or process steel, we should be more knowledgeable in identifying or in precluding those problems, so that these defects do not get generated at all. We get a good product, the surface finish is good, internal defect is good, that is what is most important. So, now let me identify or jot down what are the essential steps of this study. I have mentioned that the systematic investigation is very important. So, I have tried to jot down what are the essential steps of this study, of this investigation. Like a doctor goes ahead, he will tell you do this test, that test. So, for our metallurgical investigation, what do we do? What are the steps? First, we should identify the location, size, shape, frequency and occurrence of defect. I have just shown typical examples of defect, whether it is a edge crack, that means crack at the edge. If this is the defect, first we have to know whether it is only at the edge, what is the extent of defect, whether it is deep, whether every lap is having the defect, that means it is a continuous, the whole edge is having defect, whether is the defect is only at one edge. These are very important to. So, identification of the location, size, shape of defect. Shape of defect means, suppose I have given you an example of transverse cracks. So, what are those shapes? What are the frequency of those defects? Are they occurring continuously? Where are the cracks occurring? At a distance from the edge, at the center of the roll product, or at a certain distance from the edge, at the edge, at one edge or both the edges, all these are important. So, the location, size of defect, shape of defect, orientation of the defect, frequency of defect, this is very important, whether they are continuous or at certain locations we only have defect, and the occurrence of defect, again continuous or sudden, discrete, these are very important. So, these are symptoms, but this gives certain indications why defect is getting generated. So, this will help us in identifying the genesis of the defect. The first point is to identify the location, size, shape, frequency and occurrence of defect. Which type of defect? What is the location? What is the size? What is the shape? What is the frequency of defect and how they are occurring? This is very important. Next, carefully observe the manifested symptoms. I have told you these are all symptoms. We must carefully observe them, first with normal eye, if it is visible with normal eye, or if it requires some magnifying glass, we should observe it without doing any destruction. That means, wherever the defects have got generated, we should try to preserve those areas. When you are cutting a small piece, we should try to preserve the defect. We have to be careful, So, careful observation of manifested symptoms means the symptoms which are getting manifested as defect should not get damaged during our investigation or study. So, careful observation without damaging them, without tinkering with them, they have to be carefully observed. Then we have cut a piece, now we have to do some metallographic observation. Maybe with normal eye itself we can see if certain constituents are present or not, or sometimes it requires optical microscope, that means we have to cut a small piece, maybe we have to see the transverse section, these are very important. Defect is mostly occurring on the surface, but it has certain depth. So, that means we have to cut a transverse section, we have to see at the transverse section how deep is the defect. Finally, where it has generated, and we come to the surface, at what depth it had got generated before it has come to the surface. So, that is very important. So, investigation using optical and scanning electron microscope sometimes may be necessary. Optical electron microscope means you can go up to a maybe 500, 700 or maximum 1000 magnification with optical lens. But scanning electron microscope, the depth of focus is quite high and you can also go to higher magnification. So, when we have a rough surface, we want to see the rough surface, we want to distinguish between the surface and the additional features on the surface, some inclusions, some cracks. So, ideally it is done by scanning electron microscope, which can distinguish between the steel surface and exogenous entrapments or cracks or any other defects, because the depth of focus is much better with scanning electron microscope. So, using that we can demarcate the defect area, distinguish between the defect, actual defect and the good surface, and that gives us certain benefits, that gives us certain clues what are those defects. Next is, suppose I find there are certain exogenous entrapments, certain exogenous material is associated with the defect. It is just not normal crack, it is just not normal surface tearing, some additional exogenous entrapment is also there associated with the defect. Now, we should know what is that constituent. As I told you, if it is an exogenous entrapment or non-metallic inclusion, we should know what is the type of inclusion, then only we know where from it has come. So, that is done, that means the identification of the nature of non-metallic inclusion or exogenous entrapment, it can be done with the help of, we call it some attachment of scanning electron microscope, we call it WDX or EDX attachment. Now, what is it? WDX means wavelength dispersive, WDX, it is not WDW, it is WDX, that means wavelength dispersive analysis of X-ray or energy dispersive analysis of X-ray. Now, I will try to explain what is happening. In scanning electron microscope, also all of you possibly know, like optical microscope, optical ray is impinged on the sample and you get an optical image. In scanning electron microscope, in place of optical rays, we are using electrons. Electron beam is falling on the surface and we might get an electron image, we might get some other image also. Now, when electron is getting impinged on the steel sample, what is happening? Depending on what are the elements present on the steel, X-rays might get generated. All of you know what is how X-rays are generated. When electron beam gets impinged on the steel surface or any surface, in fact any metallic surface or any non-metallic surface also, depending on what are the elements present in that particular alloy or particular material, every element will generate characteristic X-ray which is having a specific wavelength and energy. That means, if iron is present in steel, iron will generate X-ray of certain wavelength and energy. if carbon is present, all of us know carbon is present in steel. So, carbon will generate X-ray of having a different wavelength, different energy than iron. Similarly, if you have aluminum, if you have manganese, if you have silicon, any element, you name any element, all of these will generate X-ray of certain specific wavelength and energy. Our job is to identify either the energy or the wavelength of the X-ray which are getting generated. So, in scanning electron microscope, we are impinging electron beam on the sample, and depending on what are the elements present in the defect area or even in the normal steel, X-rays will be generated. Now, the job of this attachment, whether WDX or EDX, is to segregate the X-rays based on their wavelength or energy. If the segregation is done, dispersion is basically means segregation. We are identifying separately, we are separately discriminating the energy levels or the wavelength levels of the X-rays. So, from there you can know for a particular, because it is known that if iron is present, it will generate X of certain energy and certain wavelength. If carbon is present, it will be different, the wavelength and energy will be different. Manganese is present, certain wavelength and energy. All of you know that K alpha, M alpha, L beta, it depends what are the different X-rays getting generated, for all elements are different. So, if the wavelength of the X-rays are used to discriminate between the elements, then it is called WDX, that means wavelength dispersive analysis of X-ray. If the energy of the X-ray is used to discriminate the different elements, then an attachment is called EDX, energy dispersive analysis of X-ray. So, this attachment which is available in scanning electron microscope is very handy. Most of the scanning electron microscope these days have this attachment, either WDX or EDX, and we can know what are the constituents, what are the elements present. Suppose I am exogenous entrapment, that means NMI, non-metallic inclusion, which is different from steel. Suppose this is aluminum oxide. In steel, we are not supposed to have much of aluminum. Aluminum will be there in a very, very small quantity, maybe 0.2, 0.3 max, but we find lot of aluminum is present in the steel through X-ray. Where from it has come, and we find that lot of oxygen is present in the steel. It is not there, it is not supposed to be present in normal steel, in a clean steel. So, we know from aluminum and oxygen presence of these two elements that it may be aluminum oxide. From the stoichiometry we can find out what are the constituent. If we find maybe aluminum silicate is present, that means Al2O3 and SiO2 is present. We may find manganese silicate is present. We may find some other silicate is present, calcium silicate is present, calcium oxide SiO2 is present. So, from these attachments we know what are the elements present, and from there it is possible to know what is the constituent present. And if we know what are the constituents present, depending on our knowledge of steel making or casting, we can identify where from it has come. We know, we will discuss this in details in future lectures, that we will identify, from this we know what are the genesis, where from it has come. Has it come during steel making stage, at what stage of steel making, at what stage of secondary refining, whether it has come from slag, non-metallic inclusions come from refractory, it can come from slag, it can come from other exogenous sources. So, first we should know with scanning electron microscope attachment WDX or EDX what are those elements present, then only we know what are those constituents. That will give us the right clue, that is what is important. So, after all these things what do? We have identified the location, say size, shape, frequency, occurrence of defect. we have carefully observed it, normal eye, what are the symptoms present. Then we have done metallography investigation with either optical or scanning electron microscope. What are the maybe without etching, first we have to see, after etching we have to see, because etching will help us in identifying what are the constituents present, what are the microstructure in steel, normal steel, and near the defect whether the microstructure is same, whether there is a grain coarsening, whether there has been decarburization, that means in steel certain constituents are present, microstructure is present, whether the microstructure is different in the defect area. How do we know? Through optical microscopy, through scanning electron microscopy we will know. Whether exogenous entrapments are present, how do we know? We can look at it in optical microscope, we can look at it under scanning electron microscope. So, we have to see what are the microstructure, how is it different in the defect area, what are the constituents present, whether there has been decarburization, whether there has been grain coarsening. So, all this we have to identify through microscopy. So, metallurgical investigation helps us. So, after getting all this information, whether the microstructure has changed in the defect area, whether there are exogenous constituents present in the defect area, what is the type of that constituents, whether it is oxide, whether it is sulphide, whether it is oxysulphide, whether it is nitride, whether it is a titanium nitride, titanium oxide, or calcium oxide, calcium silicate, manganese silicate, we can know everything with these attachments. So, after we have done these studies, then what do? We now try to identify where from these have come. So, for that we should know what is the steel, how the steel has been made, whether at all there was a process variation, we know how the steel has been made. So, now process variation, process modeling is very important, process mapping is very important. In secondary refining, which process was used, what was the temperature distribution in the process, what was the vacuum level, if at all vacuum was used, what was the level of argon purging, how long it was used. So, all these will give us a clue whether there was an some aberration in the process, suddenly there was a process variation, all these will be noted if the process is mapped properly. So, whenever there is an abnormality in the process, there is a process aberration, process variation, so there must be some documentation. So, we have to carefully correlate with that. So, all these will finally tell us where from the defect has come. So, that will enrich us, that will increase our knowledge, increase our expertise. So, in future we know the process has to be slightly different, the process aberration has to be arrested. Whenever there is a process aberration, we have to either control it, or if it is beyond control, that means we know that this particular heat during this particular casting stage there is a possibility of defect generation. So, maybe we have to separate out that particular cast product, this particular area of the casting has to be, because we know there is a possibility of defect generation. So, knowingly we should not allow the defect area to be processed further, because we know that further if we process it, the defect will be generated. Our level of knowledge today in most of the good steel makers have come to a stage, during the process itself one can identify which type of defect will get generated. This is based on lot of studies, lot of post-mortem studies, lot of metallurgical investigations, lot of process modeling, all these correlation, different grades, how defects are generated, different processes, how defects are generated, the variation in process, variation in secondary refining process, variation in the casting process, continuous casting process, how the defects are generated. Today people are much knowledgeable. So, from the various processes, the variation, the process mapping, people can know that defects are going to be generated at certain locations. So, our job is to stop such variation, or even if the variation is there, then identify the location where the defect will be there and separate out that defect prone areas. I think in this today's lecture, I have just shown some typical examples, some typical common defects, how they are generated, how they look like rather I have mentioned. These are very common defects, and how we go about in investigation. What are the steps in investigation? These are very essential. Systematic investigation only will give us the clue, give us the genesis why defect have got generated. So, in today's lecture, this is all what I had to mention, some typical defects and how we make metallurgical investigation a systematic one, proper one, what are the essential steps of study, so that finally we get a clue, finally we know the genesis of the defect, that is the purpose. Thank you very much for your kind attention.